So chapter 8 is a leaping off from chapter 7, which means if you're like, I am not understanding chapter 7 very well, then you're in trouble. Not really. It just means you're going to have to apply yourself to try and understand it more. Okay. Remember, we're pretty much always working in the normal distribution now. What's great about the normal distribution is that it's a continuous distribution. So there's not this whole worry about like if I'm trying to do 3 or greater, does that mean I put 2 or less and then subtract that from like we were talking about yesterday, right? Like there's not that with a continuous distribution. So in other words, it's just that point or less or that point or more, because the 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 probability of any one given point in a continuous distribution is considered to be 1 over infinity, or in essence 0. And so we can just take it from the point. Okay. So in the last chapter, we learned about like the idea of inferential statistics, or the idea of like making an inference, a guess, an educated guess about a population parameter from a sample point or a sample item, right? So we could be like, I can say I took a sample and then that sample had a mean of this. And so I can infer that the population will roughly have a mean of this, right? And we also did that with proportions, where I took a sample and the proportion of items in that sample, can make an estimate or an inference about the population's proportion. Okay. So in this chapter, we kind of get into saying, well, how certain am I that the population mean would be that? And maybe more importantly, is there an interval I can create that would tell me that I'm 95% certain the population mean is within that interval, right? And so that's kind of what we're getting to here is this idea of creating an interval. So from this number to this number, and then how certain we are, or how confident, that's the term from a statistics standpoint, we are that the true population parameter will be within that interval. I know, it sounds fascinating. Tell us more, Uncle Mike. Move forward so we can learn these great things. So there's really only 3 types, okay, of interval estimation problems. And that is where we know the population. I mean, where we're trying to find for the population mean, and our population standard deviation is known. Just in real life, that's rare that we would actually know the population standard deviation. Instead, we would have to take a sample and use the sample standard deviation as an estimate, which is going to give us less certainty about that. So the second is where it's finding the interval for the population mean, where the population standard deviation is unknown. Okay. And then the third is finding the interval for the population proportion. So just so it's not too confusing, okay, I'm saying find the interval. In the last chapter, what we're doing is trying to find what did they call them? Point estimate, I think was the term they used, right? So what is the point estimate for the mean of the population? It's the mean of the sample, right? That's the point estimate. But instead of using the population standard deviation, we would find the standard error of the mean and use that, right? I mean, that was that whole process. So here we're just saying, what is instead of the point estimate, what is the interval of the point estimate from this to this, that we can be more certain that the population parameter, the population point of interest, falls within that interval. Then the other thing we're going to learn about in this chapter is, well, how big of a sample do I need to actually do this, right? So if I want to be 95% confident that I can come up with an interval that will find the population mean, then how big of a sample do I need to do that? Okay, so that's what we're covering. So the first thing we need to know is there's this term which is called the margin of error. And so when all the margin of error is the amount plus or minus the point estimate that's going to create our interval. Okay, so we take our point estimate plus or minus a given margin of error, and that will give us this range, or this interval, where we think our population parameter is likely to be. Okay, so when we know the sigma, or when we know the population standard deviation, we're going to follow this process. And they actually call it a sigma known case, or a case where the population standard deviation is known. So we know that, let's see, I'm trying to think of the best way to attack this. So here we have a normal distribution, and we're showing a point or an interval that includes 95% of all the values. Okay. So 1 minus alpha is the probability that a value of a sample mean is going to be provided in the margin of error. Okay. And so this number right here, 95%, we're going to call that our confidence level. It'll say something like, what is the interval in which we are 95% confident the population mean will fall? So the number outside of that confidence interval is called the alpha. And it's just denotated with a lowercase Greek alpha. Okay. So if we have a symmetrical interval, I want you to recognize that the two tails together, here and here, they constitute the alpha, or 1 minus the confidence level. Okay. And so the left tail is going to be alpha divided by 2, and the right tail is going to be alpha divided by 2. So if the confidence level is 0.95, or 95% of all values, then the left tail is going to be 0.025, and the right tail is going to be 0.025. So that all of it together adds up to 100% of the distribution. Okay. The reason this is important is we have to recognize that when we have what's called a two-tailed distribution, which all normal distributions are, they have a left tail and a right tail, and it's symmetrical, that the space outside of the confidence level, the alpha, is always going to be alpha divided by 2 on the left and alpha divided by 2 on the right. And the reason that matters is our formula, okay, it's the z-score of alpha divided by 2 times the standard error of the mean. Okay, so if somebody says, so this is really confusing, but it's kind of what I just explained. Okay, so let's just go here. So here's the formula for the interval estimate of the population of the mean. So X bar, which is the sample mean, plus or minus the z-score of alpha divided by 2. So if we did 95% confidence, 1 minus the confidence level is our alpha, 0.05, divided by 2, 0.025. Okay. So the z-score of that, norm.s.dist of 0.025, that's the z-score we're looking at, times the standard deviation divided by the square root of n, and you will probably recognize standard deviation divided by the square root of n as the standard error of the mean, right, that we learned in the last chapter. So that is it. So it's pretty easy. You take the sample mean plus or minus this z-score times the standard error of the mean. This part right here, the z-score times the standard error of the mean, is called the margin of error. So it's just the sample mean plus or minus that. What's super dope about that is there is a function that will automatically calculate the margin of error for us. It's called confidence.norm. Okay, and we'll see it in a minute here. All right. So for a confidence level of 90%, we would say our alpha is 0.1, or 1 minus the confidence level. So if someone says you want to be 90% sure that the population parameter exists within this estimate you make, you use 90% confidence level, which would give you an alpha of 0.1, an alpha divided by 2 of 0.05, and then the z-score of that, which you could find with norm.dist of 1.645. Actually, norm.inverse, right? confidence level, but these are ones that get used a lot in science, either a 90% confidence level, a 95, or a 99. And so people just memorize them if they use them all the time, because I know that my Z of alpha divided by 2 is always 1645, 1960, or 2.576. But sometimes it'll throw you a curveball and be like 97%. Easy. I just take 1 minus 97%, it's 0.03, divided by that by 2, and then norm.s.inverse. I will tell you that they always want the positive value because you're doing plus or minus. So I usually do the absolute value of norm.s.inverse of 0.025, which you'll see when we do some. All right. So here's what we mean by confidence level. I won't read it all to you. But kind of what I just explained again. All right, so here's an example, Lloyd's department store. Each week, Lloyd's selects a simple random sample of 100 customers in order to learn more about what they spend. So they surveyed 100 customers, obtained a sample mean of $82. Based on historical data, Lloyd's assumes a known value of population standard deviation of 20, okay, $20. So if our confidence coefficient or confidence level is 0.95, in essence, we're going to say, well, what's an interval that we think we're 95% confident that the population mean would fall within? So it really is as simple as taking the Z of alpha divided by 2 times the standard error of the mean. So the Z of 5% divided by 2, so the Z of 0.025 is 1.96 times 20 over the square root of 100 gives us 3.92. So that is our margin of error. And then to find the interval, we just take the sample mean plus and minus it. So we are 95% confident that this interval, $78.08 and $85.29, contains the population mean. What do you think would happen if we upped our confidence level? Would the interval get wider or narrower? Now think about it. If we want to be more confident, right? So we'd have to throw our boundaries out wider if we want to make sure we capture it. Okay. So I know it was kind of a trick question, but so the higher we make our confidence level, the wider the dispersion of our interval. Okay. One before. So the 20 is the standard deviation, population standard deviation, and the 100 is the n. So it's this population standard deviation divided by the square root of n. Does that make sense? All right, good. All right, so there's our interval estimate. Here's the Excel functions. So the margin of error is just confidence.norm, where D9, which is the significance level, comma D7, which is the population standard deviation, comma D4, which is n, the sample size, and it'll give you the margin of error. And then your point estimate, which is just sample mean, the lower limit, which is the sample mean minus the margin of error, and the upper limit, which is the sample mean plus the margin of error. Okay. If you didn't have confidence.norm, you could still figure out the z-score of the alpha divided by 2, right? And then multiply that by the standard deviation divided by the square root of n. So you could still do it. It would just be another step. Okay. All right. So here we can see as we up our confidence level, our interval gets, so our margin of error, that's interesting. I wonder if that's an error. See how that dropped right there? I'll have to look at that. But typically our margin of error gets bigger and therefore our interval gets bigger. All right. So most of the time, as long as we have an n, a sample size of greater than or equal to 30, we're good, especially if we know that it's normally distributed. If it's skewed and we don't know for sure if how normally distributed it is, skewed means like squished to the side or whatever, then usually a size of 50 or more is sufficient. Okay. If it's not normally distributed, but it's roughly symmetric, you can still use these numbers. It says you could even go down to 15. And if it's believed to be approximately normal, then we can use less than 15. But for most things, taking a sample of 30 is pretty doable. Okay, and even taking a sample of 50, it's not that expensive. And so if you hit 50 or a sample of like 100, you're golden as far as saying it's going to follow roughly a normal distribution. So a normal distribution will suffice. Okay. All right. Now this is just so now the question is, what if we don't know the population standard deviation, which again in real life is almost always like, I don't know. So when we don't know the population standard deviation, they call it a sigma unknown or a population standard deviation unknown case. And so here we're going to use a different distribution. Instead of the normal distribution, we're going to use a distribution called the t distribution, or sometimes it's called the student's t distribution. I don't know why, but that's what they're going to call it. Okay. So a t distribution is similar to a normal distribution, but it adds an additional parameter called degrees of freedom. And that's the number of independent pieces of information that go into the computation of the standard deviation. In other words, our n, small n, sample size, is going to factor into this, okay? So the larger the sample size, the more closely the t distribution resembles a normal distribution, okay? Let's see. As degrees of freedom increases, the difference between the t distribution and the standard normal probability distribution becomes smaller and smaller, which is just what I said. So you can see when we have 10 degrees of freedom, it's shorter and wider, more dispersed than a normal distribution. At 20, it's starting to look a lot more like it, but it's still shorter and wider. And then if we get above about 30, it's usually about the same. Okay. And if you had 1,000 or something, it would really be super duper close. So this says for more than 100 degrees of freedom, the standard normal z value provides a good approximation of t values. All right, that's good enough. So here's how we do an interval estimate for the population mean if we don't know the population standard deviation. So again, as you attack these problems, question one is this a mean estimate or a proportion estimate? And then if it's a mean estimate, question two is, do I know the population standard deviation or do I not know the population standard deviation? And if you can create a decision tree like that, it makes these way easier, okay? So we have X bar, so the sample mean, plus or minus t of alpha divided by 2 over S, which is the sample standard deviation, divided by the square root of n. So again, we can recognize this standard deviation divided by square root of n as the standard error of the mean, okay? Except that we don't know the population standard deviation, so we're going to use the sample standard deviation as an estimate, and that's what forces us into using the t distribution, which has more dispersion, which gives us a wider range to our interval. So here's a credit card debt for the population of US households. The credit card balance of a sample of 70 households provides a mean credit card debt of 9,312 with a sample standard deviation of 4,007. Let us provide a 95% confidence interval of the mean credit card debt, blah, 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 blah. Okay. So in this case, it does not give us a population standard deviation. So this would be a sigma unknown case. Okay. So what they show here is there's a table where you look at the area of, so this is the z of alpha divided by 2 and the number of degrees of freedom for all of these problems, degrees of freedom is always going to just be little n, sample size, minus 1. So that's easy to remember. So if we have 70 items, then our degrees of freedom will be 69. Okay. So this is one way. If you have this table, you can just look and be like, okay, so that's our t of alpha divided by 2, or we can just use confidence.t to give us the margin of error, or to find this number, we could use t dot inverse. Okay, so same thing as norm, it's just t. So it just needs a little practice to work with it. So again, you take your t of the alpha divided by 2 times s divided by the square root of n. That gives us your margin of error, which is 955. So then our interval is 9312 plus or minus 955. All right, there's another little tool in Excel you may want to play with. It's called the descriptive statistics tool. We'll have to look. When they used to have these computers set up, you couldn't, the data analysis tool pack wasn't set up, and you had to go in and like set it up, and then at midnight it would wipe the computers and you have to set it up again each day. So when we do the guided, I'll show you how to set that up, but if it's not in there. But we can go to the data tab on our ribbon. If it's your own computer, you can set it up once, and then you always have this tool. And then you go to the analysis group, click data analysis, and choose descriptive statistics. Then you enter the input range and so forth, and it will just give you this output that's hard to see because of the size of it, but it's kind of awesome. I use it a fair amount. It'll give you the mean, the standard error of the mean, the median, the mode, the standard deviation, the sample variance, other stuff like kurtosis and skewness, which we're not even that concerned about right now. It'll give you range, minimum, maximum, the sum, count, and the confidence level. Like, so kind of awesome. Like, it just gives you this summary output of a bunch of things. So again, when we do one, I'll walk you through kind of how that works so you can see it and decide if it's a tool you'd rather use. Or honestly, for most of the work we do in this class, I think the output is too much and it would just be confusing. I don't know if that makes sense. It would give you too much info and then you'd be like, which one do I look at? Easier to just put in the function you need when you only need a couple things. But they just wanted to show you in this chapter that this is there, I guess. All right, so here's our summary. They do it as a flow chart, right? Summary of interval estimation procedures. Can the population standard deviation be known or be assumed to be known? Yes. Then use the x bar plus or minus the z alpha divided by 2 times population standard deviation divided by the square root of n. No, then use the t alpha. So honestly, I just want you to think these are almost identical, okay? Except this one uses the z-score of the alpha divided by 2 when we know the standard deviation, and this one uses the t-score of the alpha divided by 2 when we don't know the standard deviation. This one uses the population standard deviation because we know it. This one uses the sample standard deviation because we don't know the population standard deviation. Other than that, they're identical formulas. So the process isn't really different. It's just like, which score am I using? The z-score or the t-score is really what that's going to help you determine. All right. So now the question is, well, how much of how big of a sample size do I need in order to get the right margin of error that I want, and in order to have the right confidence level? Okay, so we know a formula already to figure out the margin of error, which is just the z-score of alpha divided by 2 times the standard deviation divided by the square root of n, right? So certainly if we wanted to, and we knew what the margin of error is that we wanted, then we could just solve that for n. Okay, that's in essence the process that's going on here. So they take the margin of error formula and they use E. I would use ME for margin of error, but they use E, okay, for error, I guess, equals that. And then they just recast it algebraically to give you the sample size. So it's just little n equals the z of alpha divided by 2 squared, population standard deviation squared over the desired margin of error squared. So if they give you a problem, this is one you'll have to do with math. Again, it's not that hard to set up an Excel calculator to do that. If you know, if it's a 4 variable problem and you know 3 of the 4 variables, it's just algebra, right? So just algebra, easy. So here's an example. Oh no, this is still telling us about it. All right, here's our example. So previous study investigated the cost of renting automobiles in the United States, found that the mean cost was approximately $55 per day, with a standard deviation of 9.65. Suppose a project director wants an estimate of the population mean daily rental costs such that there is a 95% probability that the sampling error is $2 or less. How large of a sample size is needed to make this happen? Okay, so we're going to do the z of alpha divided by 2, which is 1.96 squared, population standard deviation squared, and the margin of error of 2 that the guy wanted squared, and then we just solve it. With these, what you'll normally do is just round typically up to the next whole number, right? Because when you're talking about what's the sample size, you can't have a partial sample, and it's better to take one more person in the sample than one less. Does that make sense? So the sample size needed is about 90 rentals in order to satisfy the project director's $2 margin of error requirement. You'll see a couple problems like this. All right, last thing, kind of feel like I should put that at the end, because the other one is population proportion. So it is the P bar sample proportion plus or minus a margin of error, okay? So the sampling distribution of P bar can be approximated by a normal distribution. Again, we've already done proportions in the last chapter. So we know what a normal distribution looks like. We've already learned the standard error of the proportion, this part right here, right? The proportion times 1 minus the proportion over n, take the square root of all of it. So it's just the z of alpha divided by 2, the z-score of 1 minus the confidence level divided by 2, times the standard error of the proportion. And then that's plus or minus the sample proportion. So again, this shouldn't be crazy hard unless you were completely lost in the last chapter, but it's okay if that's true. You can get caught up, okay? So here's an example. National survey of 900 women golfers was conducted to learn how women golfers view their treatment at golf courses in the United States. The survey found that 396 of the women golfers were satisfied with the availability of tee times. Suppose one wants to develop a 95% confidence interval estimate of the proportion of the population of women golfers satisfied with the availability of tee times, okay? So we know that our sample proportion would be 396 out of 900. 396 divided by 900 would tell us what proportion of women were satisfied in that survey, right? We know our N is 900. What is our big N, our population? It's essentially limitless relative to the size of the sample, right? It's going to be way bigger than 900. So we're okay here. All right. So we're going to say the sample proportion plus or minus the z alpha divided by 2 times the square root of sample proportion times 1 minus the sample proportion over n. We know n is 900. We know the sample proportion is 0.44. And we know the z of alpha divided by 2 is 1.96. So now it's going to be, this whole part right here is going to be 0.0324. So our interval estimate is going to be 0.44 plus or minus 0.0324. You'll see that population standard deviation or sample standard deviation never came into play. And it doesn't with proportions, which means we don't have to worry about whether or not the population standard deviation is known or unknown, okay? So that helps. Excel functions we can use. So again, sample size, sample proportion, confidence level we would have to input. Level of significance is 1 times the confidence level. The z-value is norm.s.inverse of 1 minus d9 divided by 2. Standard error, margin of error, etc. So again, this just shows you how you can use Excel. If you ever want to look back at any of these slides, they're available in Canvas in the additional study material stuff. I have just the full slide deck in there if you ever want to. But this little picture is also in the book. Okay. If you're like, oh, I don't remember all that function. Same idea. If we want to figure out how big of a sample size we need for something like this, we know the formula for margin of error. We can just recast that formula to solve for n, and then we can figure out what sample size we need for a given margin of error. Okay. Here's an interesting thing. So the planning value of P, what we want P to be, the proportion that we want to show, it can be done by a couple of ways. If we use a sample proportion from a previous sample that has similar units, or selecting a preliminary sample and using that sample proportion for this sample, or using our judgment for a best guess value of P. Otherwise, we use 0.5 as the P value when we're finding this. Here's the reason why. If we don't know, then 0.5 is the middle proportion, okay? And it actually is the most, what would you say in accounting? The most conservative estimate is that the proportion is split evenly. And so this would give you the highest value of n, which would mean that you'd be sure to have enough in your sample size to get the margin of error you want, okay? So if it doesn't tell you in a problem, this is the value to use for P, then you're going to use 0.5. That might pop up and you'll be like, oh, he told us that and I totally forgot, because why would I remember a factoid like that? All right, so we're going to suppose the survey director wants to estimate the population proportion with a margin of error of 0.025 at 95% confidence. How large of a sample do they need? This one says a previous sample of similar units yielded 0.44 for the sample proportion. So we're going to use 0.44. Okay, so we're going to do the z of alpha divided by 2, which is 1.96. Use 0.44 for the proportion, 1 minus 0.44 over the 0.25 margin of error, 0.025, and we'll solve. And for this one, we see we need a pretty good sample size, right? We need like 1,514 in that sample size to get the margin of error we want. It's a big honker of a sample. And that's it. So this chapter is pretty doable, especially for smart people like you guys. And I hope that you have a terrific week. What? Hold on, let me pause this.